Welcome physics students to today's video. Today's video will be looking at mass defect and energy calculation for an alpha decay equation. This video is one of three in a series. The first video examines mass defect and energy calculation with nuclear fission. The second, which we're looking at today, involves the mass defect and energy calculation. And the third video once again looks at mass defect and energy calculations in the context of fusion. So let's look at today's video. So on the screen you can see we have an alpha decay equation. We have uranium-238 that decays into thorium-234 by giving off an alpha particle, and in the process it gives off considerable energy. We also have the 1, 2, 3 masses for the isotopes shown in the above equation. The task for today, number 1, is to calculate the mass defect, and number 2, calculate the energy generated from the mass defect. So task number 1, to calculate the mass defect for the equation shown on the screen. First of all, let's look at the mass of the reactants. The reactants in this equation are highlighted in green, and there's only one, that is uranium-238. So we use the value given to the left. It is a mass of 3.95293 by 10 to the negative 25 kilograms. Let's now consider the mass of the products highlighted blue. We have two isotopes here. One is a helium-4 nucleus, or an alpha particle, and the other is a thorium-234. And the mass of each is given in the data set to the left. That tallies to a total product mass of 3.952848 by 10 to the negative 25 kilograms. And as you can see, comparing that to the mass of the reactants, it's slightly less. It would appear that mass has disappeared. This is what we refer to as the mass defect, the difference between the mass of the reactants and the mass of the products. By subtracting these two values, we find the mass defect for this particular alpha decay to be 8.24200 by 10 to the 30 kilograms. This mass defect is extremely small. However, this is for one single nuclei decaying. So when you consider the billion of nuclei present in a sample of uranium-238, this accumulates into a significant amount of energy. So our mass defect was found to be 8.24200 by 10 to the negative 30 kilograms. Our second task was to calculate the energy generated. And this is Einstein's work. Einstein was the one that proposed that energy and mass equivalent. So we can convert that mass defect into energy. So E, the energy, is what we're trying to calculate. M is the mass defect, 8.24200 by 10 to the negative 30 kilograms. And C, the speed of light, is 3.0 by 10 to the 8 meters per second at the VCE level of studies. We're using Einstein's equation, E equals mc squared. We substitute our values in, that is the mass defect and the speed of light squared, and we get an answer of 7.41780 by 10 to the negative 13 joules. Hard to visualize 10 to the negative 13 joules, and for that reason nuclear and particle physicists use the unit of electron volts, or indeed mega electron volts. So let's now convert that small amount of joules into both electron volts and mega electron volts. So to do so, we take our value in joules and we divide it by 1.6 by 10 to the negative 19. This is a simple conversion to change from joules into electron volts. That gives us a value of 4,636,125 electron volts. If we divide that by a million, we can of course express this in mega electron volts. So to go from electron volts to mega electron volts, we divide by 10 to the 6, or effectively move the decimal places 6 places to the left. That gives us an answer of 4.636125 mega electron volts. So the energy created in this alpha decay equation is 4.636125 mega electron volts.